Question 19 begins with a Hess's law question. The important thing with these is that you've got to look carefully at the data, and especially you've got to know for sure what enthalpy change of formation and enthalpy change of combustion mean, so that you can translate that into a picture. So in this question we're mainly given enthalpy changes of formation, and when you have a formation cycle, the key is to remember that enthalpy change of formation means the enthalpy change when you form a mole of a compound from the elements it's made up out of in their normal standard states. So your cycle is going to be based around that you're going to have the elements at the bottom, and then you're going to put on the enthalpy changes of formation, which are going from those elements to form the products. Now, the equation that's going to go across the top, that's going to provide the sort of line on which this whole thing is based, is the combustion of ethanol, because that's the number we're given, the enthalpy change of combustion of ethanol. That's the only number that isn't a formation enthalpy. So the next job, I guess, is to write the equation for that. So ethanol is C2H5OH, and that's reacting with some oxygens to give you carbon dioxide, let's balance it in a second, and water. Because that's what always happens, remember, in enthalpy change of combustion. It's complete combustion to give CO2 and water. Now, that equation has got to be balanced. This whole calculation will be meaningless if it's not based on a balanced equation there. So that's crucial. And it's an easy one to balance, because we've got 2 carbons in ethanol, they both end up as CO2, so that's got to be 2. We've got 5 plus 1 is 6 hydrogens in ethanol, they all end up as water, so that's 3 lots of 2, 6 hydrogens altogether on the right. That just leaves this number, which actually we don't really need, but just for completeness we'll put that in. So we've got 2 2s are 4, plus 3 is 7 oxygens altogether on the right. One of them is there, so we need 6 more, so that's 3 O2. So that's the equation for combustion, and so we can put our first number on the diagram now, because it tells us that the enthalpy change of combustion, which is the enthalpy change for that reaction, is minus 1367 kilojoules per mole. So we can put that on there. Then we can start to put these enthalpy changes of formation on, because it tells us that the enthalpy change of formation of ethanol is minus 279 kilojoules per mole. So that means when we go from the elements to form a mole of methanol. So you can see lots of people worry about not knowing which direction the arrow should go in, but the definition tells you it's the enthalpy change when you go from the elements to form a mole of whatever substance it is. So that tells you which way the arrow goes, and that's minus 279 kilojoules per mole. Oxygen, of course, doesn't have an enthalpy of formation because it's already an element, so no problem with that one. Coming up to this side, we've got 2 things going on there. Now the water we've got a number for, because it tells us delta H of formation of water is minus 286 kilojoules per mole, but this is where the balancing comes in. There were 3 waters, not just 1, so on this side it's minus 286 times 3, because we're going from the elements to form 3 moles of water, and we're forming 2 moles of CO2, and that's what the question wants us to find out. What's the enthalpy change of formation of CO2? So what we can say, let's call X the enthalpy change of formation of CO2. Okay, so we'll just define that as being X, and so we can say, well, here we're making 2 moles of CO2, so that's plus 2x. Now is where Hess's law comes into play, because Hess's law says that it doesn't matter what pathway you take for a reaction, the overall enthalpy change is the same so long as the initial and final states are identical. So what that means is that top reaction takes minus 1367. So if we do an indirect route like this, which involves breaking up these things to make the elements and then recombining them to make these compounds on the right, the sum of those 2 steps will add up to the same thing, minus 1367. So we look at the two steps. Now the first step, which is this one here, you can see it's just the exact opposite of that. So this time we're unmaking these compounds, turning them back into the elements. So because we're going the opposite way, we change the sign. So that will be plus 279 going that way. The second leg is exactly the same as that. You can see we're going in the same direction, we're doing exactly the same thing. So going up there will just be those numbers again. So what we can do now is equate those two things following Hess's law and say minus 1367 equals the sum of these terms here. So let's write that down. We have that minus 1367, according to Hess's law, is equal to plus 279 minus 3 lots of 286 plus 2x. Okay, and now it just becomes a little bit of rearranging to turn that into something that gives us the value of x. So if we just rearrange that slightly, we get that moving this term over, or both these terms over to that side, we get that minus 788 is equal to 2x. Okay, so we've just subtracted 279 from each side to make it disappear from here, and then added 3 times 2h6 to each side to make it disappear from here. Okay, so we've got to take this number minus 279 plus 3 times 286 gives us that, and that's equal to 2x. So we therefore just divide that by 2, which gives us minus 394 is equal to x. And that's our answer, but obviously we've got to write it more formally. That's just a number at the moment. So we've got to say that the enthalpy change of formation of CO2, which is what we defined x to be, is equal to minus 394 kilojoules per mole. And that's the answer. Part B then is about this, which is the Sabatier reaction, and it wants first of all an expression for Kp. For this, be careful with equilibrium questions, make sure whether it wants Kp or Kc, don't go off in the wrong direction, but this one wants Kp, so you just follow the usual recipe. Stuff on the top goes on the right, so it's the partial pressure of methane times the partial pressure of water squared, because there's two of them, divided by the partial pressure of CO2 times the partial pressure of hydrogen to the power 4, because there are 4 of those. So that bit is easy. The next part is asking us to consider why you would use these conditions to operate this process for producing water. And it's important to remember you're trying to produce water, so you want to maximize the production of water when you operate this process on a spacecraft. So you get a lot of questions like this. Usually they're not about spacecraft, they're about industrial processes, but the principles are the same. So the important word in any question like this is going to be compromise. Okay, because your choice of conditions, and that means temperature and it means pressure, it's always going to be some kind of compromise, and what you have to establish is what that compromise is. Okay, so that's the way to structure things. So always consider both the pressure and the temperature. Okay, so we've got to consider pressure and temperature, and for each of those you have to consider really 3 types of issue which might dictate which value you end up choosing. The first is the equilibrium yield, and that's about using Le Chatelier to decide whether you want high or low temperature or high or low pressure to shift it in the direction that you want it to go. You have to consider the rate of reaction, because there's no point having an incredibly high equilibrium yield if it takes you years and years to get there. It's got to happen at a reasonable rate. And sometimes if both of these kind of agree with each other, so for example if they both say yeah you want high pressure, you have to think, well yeah, but why wouldn't you go to sort of incredibly high pressure? There must be some limit on that. And so sometimes you need to consider cost and safety as issues which might put a limit on what you want to go to. Okay, so these three aspects are what any question like this, the answer needs to be based around. So make sure that you sort of learn this as a general approach. So let's do the pressure first of all. And just think about each of these in turn. So in terms of equilibrium, Le Chatelier says that it will, if you go to high pressure, it will shift in the direction where there are fewer moles of gas, because that will oppose the change. And you can see these are all gases, by the way. It tells you that in the question. So you've got 5 moles of gas on the left, 3 moles of gas on the right. So high pressure will shift it to the right because there are fewer moles of gas. Okay, so high pressure will give a good equilibrium yield of water, because that's what we're trying to make. And just give a brief explanation. Obviously you can't waffle on forever on these things, but you just sort of say that that's to opposes, or shifts to the right, I suppose we could say. Because there are fewer moles of gas. Just give us a brief explanation like that. Fewer moles of gas. Right, so that's the first point. Then what about the effect of high pressure on rates? Well, the higher the pressure, the closer together the molecules are, so the faster they'll react. So high pressure also gives a faster reaction. And again, just briefly say, because the molecules are closer together. And then you can see we've got one of these situations where both of these things say, yeah, high pressure is good, because we get lots of water and we get it quickly. So the limit is going to be the cost and safety. In the case of a spacecraft, it's going to be mainly the safety. Okay, so we can say that it would be unsafe to go to too high pressure. So 30 atmospheres is a compromise. And try and put that word in explicitly so that they can see that you realise that that's what chemistry on the practical scale tends to be all about. Okay, so that's the pressure side sorted out. Let's have a look at temperature then. And just process it in the same kind of way. So if we're looking at temperature and go through the same things, equilibrium yield, well, it gives us the value for delta H. It tells us delta H is negative, which is exothermic in the forward direction. So high temperature will shift the reaction in the endothermic direction. Remember, if you increase the temperature, it tries to cool it down again, and it does that by going in the endothermic direction, which takes heat away. And the endothermic direction is backwards, so that's bad, right? Because if we go to high temperature, it will shift in the backward direction, so the yield of water will be low. Okay, so high temperature will give a low equilibrium yield. Of water, and the brief explanation is that it shifts to the left because this is the endothermic direction. Okay, so far high temperature sounds like a bad thing, so we're going to want as low a temperature as possible. But in terms of rate, of course, high temperature is a good thing, because high temperature will increase the rate. So high temperature, but it will increase the rate. Of forming water. and that's the usual thing about more frequent successful collisions. So this time we've got a compromise already, because equilibrium says you want the temperature to be low, because that will shift it to the right, but on the other hand rate says you want the temperature to be high, because that will produce the water quicker. So that's where your compromise comes. So you say, so 300 degrees C is a compromise, and just spell that out a little bit more. So it's high enough for a reasonable rate, without shifting too far to the left or in the backward direction. So shifting too far to the left. Okay, so they can carry quite a few marks when you get those questions, so remember that general approach. Always base it around finding the compromises. Think about both pressure and temperature, and for each of them discuss equilibrium, yield, rate and cost and safety if necessary. We didn't do that for temperature because we already had a compromise. Obviously that would come as part of the equation as well in reality, but if you've already got a compromise you don't really need to talk about that in an A-level question. Part 3 asks us to calculate the value of Kp from some experimental data. As soon as you see that you have a question like this, you need to set up a table. And across the top of the table you write the equation for the reaction. And then what you put in it, first of all, are the initial moles and the equilibrium moles. And you should have enough information in the question to let you get those. So in this case, it tells us that at the beginning we have, what do we have? 1 mole of CH4, so we can put 1 in here. And it tells us that we have 4 moles of H2O, so we can put 4 in there. So 4 moles of steam. It doesn't say anything about having CO2 and hydrogen, and that's because there isn't any, so we can put zeros in there. Okay, so that's what we had at the beginning. 0 each of those, 1 and 4 of those. Now at equilibrium, it tells us that we have 0.2 moles of CO2. So we've got 0.2 moles there. So our first job then is to fill in the rest of those numbers. And you do that by just looking at the size of this change. And you say, yeah, okay, that went up by 0.2 moles. And then you use the equation to figure out what the changes in all the other ones must be, because that's what the equation does. It relates the relative number of moles of each substance that react or are formed in the reaction. And so specifically it says that if this one goes up by 0.2, this one will go up 4 times as much, because one of these is produced at the same time as 4 hydrogens. So this will go up 0.8 times, sorry, by 0.8, because it's going up by 4 times as much as the CO2. So that will go to 0.800. The ones on this side, of course, will go down, because if we're making more of the stuff on the left, we're going to have less of the stuff on the right. So this one's going to decrease, and you can see every time 1 CO2 is used up, or formed rather, in this case 1 CO2 is formed, 1 CH4 is used up. So if this goes up by 0.2, this will go down by 0.2, which gives us 0.800 for that one. And again, the 2 comes into play here. So we're going to make or use up twice as much water as we do methane. So that's going to decrease by 0.4 rather than just 0.2. So that's going to go to 3.60 moles. Okay, so that's the first job. And that would be the same whether we were doing Kp or Kc. Now the next thing is to remember that because we're dealing with Kp, we now need to turn these actual numbers of moles into mole fractions. So that's the next line in the table. is to put the mole fraction there. And to calculate that, remember, we add up the total of all of these moles and we divide each of these numbers by that total. Okay, so that's just dividing by the total moles. So if we add these up, we get 0.2 plus 0.8 is 1, 0.8 plus 3.6 is 5.4. So we're going to divide each of these numbers by 5.4, and if we do that, we get 0.0370, 0.148, 0.148, and 0.667. Those mole fractions should add up to 1. So if you're wanting to sort of just check as you go along, you can just do a quick check and make sure those numbers add up pretty much to 1. Otherwise, you know you've made a mistake there somewhere. Once you've got the mole fractions, the next step is to calculate what the partial pressure of each substance is, the contribution to the total pressure that each one makes. So that's our next line, partial pressure, and that's equal to the mole fraction times the total pressure. Okay, so in other words, we've just got to take each of these numbers, which are the mole fractions, and multiply them by the total pressure, which it tells us is 4 times 10 to the 6 pascals. So we multiply each of these by 4 times 10 to the 6, and we get 1.48 times 10 to the 5, and 5.92 times 10 to the 5. Same for this one, because it's the same mole fraction. And this one is 2.67 times 10 to the 6, because it's a bigger mole fraction, so a bigger partial pressure. So we've now got the pressures of each substance, and they're ready then to go into the Kp expression, which we've already written down earlier on. So we take stuff on the right first, so we get 5.92 times 10 to the 5 times 2.67 times 10 to the 6 squared, because we've got the 2 waters, so that number needs to be squared. And then on the bottom line we have 1.48 times 10 to the 5 times 5.92 times 10 to the 5 to the power 4. Okay, so don't forget to raise those numbers to the appropriate powers. That's a very common mistake, is even when people have written it down there, they don't always enter it into calculators, so make really sure you've done that. If you crunch all of those numbers together, you should get 2.32 times 10 to the minus 10. Okay, now you're almost there, but you've always, as in any calculation, when you get the final answer, you've always got to stop and think, does it want units? In this case, the question actually told you it wanted units, but even if it doesn't, it's your responsibility to sort those out. So the recipe that we have says that what you should do to calculate the units of an equilibrium constant is calculate a number x, which is just moles on the top minus moles on the bottom in your Kp expression. Okay, so in our case, this is what's on the top, so you've got 2 plus 1 on the top. These are on the bottom, so you've got 4 plus 1, so you've got 3 minus 5. So x is equal to minus 2. And for Kp, the units are simply pascals or kilopascals, whatever it is you're working in. In our case, it's pascals to that power, so it's pascals to the minus 2. And that's our unit. So make sure you learn those recipes. You've got this one, you've got the very similar one to learn for Kc, or again you calculate the same x, and then you've got also the recipe for the units of a rate constant. You know, they're always only going to be 1 mark, but it could be the 1 mark that makes all the difference, so it's worth learning those recipes.